All right, so we're continuing on with electric circuits, and we looked at two different values last day, where we looked at voltage and current. And now, again, just to recap, voltage is how much energy your charges have that are flowing through the circuit, and your current is how many of those charges are being sent through the circuit per second. Now, we're going to look at a third value today. We're going to add in and we're going to do some calculations, and then we're going to include this into our circuit diagrams. And it's called electrical resistance. And this is a gentleman's, we're going to look at Ohm's law. And what happens is when charges pass through a device, the load as they call it, or the lights, appliances, they experience a resistance to their flow, resulting in a loss of electric potential energy. Since each load resists the flow of charge differently, each load has a unique resistance. And again, resistance, I always like using the analogy with electricity is that it's like water flowing through a river. And in cases of resistance, what you're looking at is maybe there's rocks and trees or something that are slowing down the flow of the water. And that's the same thing with electrical resistance, only the thing that's slowing down the electricity from flowing is the things that are using the energy. So again, every item or every load has a different resistance. Now, we have Ohm's law here, which I've created a formula triangle, and if you've never seen a formula triangle before, what this is saying with Ohm's law, because we have voltage again as V, I is our current, and now R is our resistance, is that if I'm finding V, well, then that would be just I times R. And again, this is a triangle where you can find all the values. So if I was finding I look at my triangle, V's on the top, R's on the bottom, so it would be V divided by R. And then if you're finding R, you have V on top again and I on the bottom, so it's V divided by I. And again, just to be clear here, again, V is our voltage. I is our current still. And R, of course, is our resistance. And because we're using what's called Ohm's law, resistance, the units are ohms. Now, they have a funny Greek symbol for ohms, actually, and it looks like a bit of a horseshoe. There we go. So that is our ohms. Now, I typically will use V equals IR. I just stick with VER. It's easy to remember. All right, we have a note down. So let's try some examples here. All right, so an automobile headlight has an average resistance of 24 ohms. You see that little funny horseshoe there. Car batteries provide a potential difference of 12 volts. What amount of current passes through the headlight? And so again, we have our resistance is 24. I don't have a symbol for ohms, so we'll leave that one alone. Our voltage here is 12 volts, and we're looking for the current. All right, so again, I always just like to roll with V equals I times R. All right, so this time I know the voltage is 12. We are finding the current, and the resistance is 24. This is probably one of the easiest formulas we've dealt with this year. All right, and so I want to get I by itself. So I'm going to divide both sides here by 24. And so our current is going to be 12 divided by 24, which is, well, 12 is half of 24, so it's 0.5 amps. All right, let's try one more of those. So I'm going to, let's skip this one. We'll go down here. All right. What is the resistance of a 1,100 watt hair dryer plugged into a 120 volt outlet with a 10 amp current flow through it? Whoa. Okay, so what do we got here? We're looking for the resistance. What is the resistance? All right, the power of this hair dryer is 1,100 watts. The current is 10 amps. And we're out of a standard plug, as I mentioned, in Canada anyways, and the US is 120 volts. Voltage is what comes out of our plug. All right, so we're looking for resistance. So again, I got V equals IR. The voltage is 120. The current is 10. And we're trying to find our resistance. Notice how I didn't use power. Just a little extra information there thrown in there just to make it a little tricky. All right, so then I'm going to divide both sides by 10. And, well, 120 divided by 10, well, that's going to be 12. And again, our units here are ohms. Nice little horseshoe there. All right, so now what we're going to look at is resistance within a circuit because we're tying this all together. All right, so in a series circuit, we have 3 lights in this case, so they are going to be considered resistors, as we would say. And so that's R1 here, R2, little subscript. And down here, I'll say that's R3. Now, the complete resistance or total resistance of the circuit, we call R0, or really it's R0. Now, in a series circuit, again, that's when the charges have only one path to go down. Your R0 is equal to all the resistances, R1 plus R2 plus R3 plus, if you had more, if you added lights, you'd add up all of them. So say if you had a number n of them, you just keep adding up all the resistors or all the resistors in a row. Now, in this case, there is only 3 of them. So your resistance, you would just add up R1 plus R2 plus R3. Because there's only 3 of them. If you had 10 of them, you'd add up 10 of them. Now that's for a series circuit. Things get a little tougher here when we get to a parallel circuit. Now in a parallel circuit, it's going to be a little crazy here. We have R0, which again is the resistance of the entire circuit, the combined resistance, I would say, is equal to, now we go 1 over 1 divided by R1 plus 1 divided by R2 plus, and you just keep doing that, dot, 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 till you get to the last one, which I'll write 1 over R to the N. And then I'm putting all that in brackets, and we go to the -1, to the power of -1. So that's quite the formula there. Now, let's see, let's move this over. There we go. Now, in this circuit, again, it's a parallel circuit where, again, your charges have options on which resistor they're going to go down, or each load. And so I have, again, 3 of them, R1, R2, and R3. And so to find the resistance within this circuit, which is our R0, it would equal 1 over R1 plus 1 over R2 plus 1 over R3. And then I have to do the exponent to the -1. All right. So that is how we look at a series circuit and a parallel circuit in terms of resistance. Now, in the following diagrams, find the circuit's equivalent resistance, which is a nice way of saying R0. Well, again, we have 3 resistors here, 5 ohms, 4 ohms, 2 ohms. And if I wanted to find R0, well, because it is in series, this is the best one, easiest, we just add them up. 2 plus 4 plus 5. And we have 6, 11 ohms. I can write it. For that funny horseshoe. There we go. Ohms. All right. Now, that is again in series. So now here we get to the tougher one, where we have 4 resistors here in parallel. All right. So again, I'm going to use my formula. So I'm going to find R0, the equivalent resistance of the entire circuit. And so I got R0 is equal to, now I better put in brackets here, first resistor is 8. So I'm going to have a 1 divided by the 8. Plus, the next one's a 5. So I'm going to have a 1 divided by 5. Plus, the next one, we got a 10. So we're going to have 1 divided by 10. And of course, the next one here, we have 1 divided by 5. And I can't forget to take it to the -1 afterwards. All right, to the power of -1. All right, so 1 divided by 8 is 0.13. Plus 1 divided by 5 is 0.2. 1 divided by 10 is 0.1. Plus, now I got these in my calculator here. 1 divided by 5 again is 0.2. And when I figure that out, I'm going to take it to the power of -1. All right, so I add those up. Let's see, and I'm getting, on my calculator here, I get 0.63. Again, this is to the power of -1. And when I do take it to the power of -1, I get 1.59 ohms. Now, what you might notice here is that when we did the series resistance, we add them all up and see it's 11. And so again, I'm looking at that analogy of electricity being like water flowing through a river. Well, say these are 3 trees. Well, the resistance is much higher if the water has to go through these 3 trees. But with a parallel circuit, it's like the water has 4 different paths that it can take. And so there's options there. And so because of that, the resistance is actually less when it's in parallel. All right, so now, of course, we get to the next step, mixed circuits. All right, so now we're mixing them up. And so again, I'm going to be looking for R0, which again is our equivalent resistance. Now here's the trick of this one, is I have 1, 2, 3, 4, 5 resistors. So I'm going to have R1, call this 2, 3, 4, and 5. Now 1, 4, and 5 are all in series. But what we actually have is a parallel part in series. So what I'm going to do is I'm going to combine R2 and R3 together using my parallel resistance formula. And that way they'll act as if they are just one resistor. And so what I'm going to do here is I'm going to find what's called R23. What R23 looks like or is equivalent to. And again, because they're in parallel, I'm going to take 1 over 5. And the next one here, we got a 4. So plus 1 divided by 4. And again, I have to take it to the -1. All right, now what do I got here? 1 divided by 5, I know is 0.2. Get that B out of there. 0.2. 1/4 is 0.25, 1/4. And then again, I have to take it to the power of -1. All right, so what I'm really doing is I'm taking 0.45, all right, and taking it to the power of -1. And we end up with 2.22 ohms. Again, that's something you should try out in your calculator there. That's calculation that sometimes messes people up. All right, now what I've done is I've combined 2 and 3, so they look like 1 in terms of my formula. And because now I'm dealing with all of these in series, my equivalent resistance, my R0, is going to equal R1 plus R23 plus R4 plus R5. So R0 or R0, I should say. Let's see, we have a 1, there's a 10. We found out that R23 is equivalent to looking as it's 2.22 in series. R4 is 3, and R5 is 2. I add them all up, let's see here, and I get 17.22 ohms. And there we go. So again, we had to use all our formulas, a combination here when we got a mixed circuit. I had to combine R2 and R3 in parallel using my parallel resistance formula. So now that I could calculate the complete circuit resistance acting as if it's in series. All right, and see, I think I got another one here. Yes, I do. All right. So here we go. Now, this one's a little bit different too, is that we have a series circuit inside a parallel, which is inside a series. Say that 10 times fast. All right, so again, we have a series circuit inside a parallel, which is again inside a series. And again, we're looking for the equivalent resistance. So I'm going to label my resistors again here as 1, 2, we'll call this guy 3, and we'll call this one 4. Now, the first ones I can put together are 1 and 2 because they are in series. And so what I'm going to do is figure out what's called R12. And because they are in series, I'm just going to add R1 plus R2, which in this case is going to be equal to 2 plus 3, which of course is 5. So R1, 2, I should say, is 5 ohms. All right, so that's what we've made, or what I've made this one look like. But now what I'm going to do is combine this R12 with R3. And so it will be called, because we're combining all three of them, it's going to be called R123. Now, those two circuits, or all of them again, are in parallel. So I'm going to have to use my parallel formula. So I'm going to have 1 over R12, because that's what I made the other circuit look like, plus 1 over R3. And again, to the power of -1. All right, so R123. So I'm combining all three of these. We have 1 over 5. And then what resistor 5 is 10. So we have 1 over 10 divided by -1. All right, so now let's see. 1 divided by 5, I had that a bunch of times today. That's 0.2. 1 divided by 10 is 0.1. And of course, I got to take it to the -1. -1. All right, so that means I'm going to get 0.3 to the power of -1. And I end up with my equivalent resistor here of 1, 2, 3. It's called equivalent because it represents the same thing, looks different. And I'm getting 3.33 ohms. All right, so now what we've done is I've made this whole part, I figured out that it is equivalent to looking at 3.33. All right, now let's get rid of that. Now, finally, to figure out RO, because now they're all in series, RO is going to be equal to that R123 that we figured out, plus this lonely one resistor over here, R4. And so we have 3.33 ohms plus R4, which is 8 ohms. And so the equivalent resistance of the whole circuit is 11.33 ohms. All right, and so in our next class, we're going to get into circuit diagrams, just like we did before, using Kirchhoff's voltage law, Kirchhoff's current law, but now we're going to throw in this third variable of resistance, and we're going to have to, it's like a puzzle. We have to use